Okay, so question 4 is next. I think this is probably one of the easier questions. It's a gravitational wave question, and the first part is asks you to write down the Lagrangian. Now in the question you're already given the metric which contains all the coordinates and all the coefficients, so all you have to do is recognize that each one of the coordinate pieces, dx, dy, dz, and c dt, just get divided by or differentiated with respect to detour being the parameter along the curve. And if you do that, you can write down a Lagrangian with the usual square root without really doing anything more than just inspecting the metric signature which is given in the question. So that's quite an easy set of marks. Having written down the Lagrangian, you're asked to find two constants of the motion. Again, this is fairly standard because it's clear that neither the x nor the y coordinates appear in the Lagrangian except as derivatives dx by detour and dy by detour. So if you differentiate the Lagrangian with respect to dx by detour or with respect to dy by detour, the result will be a constant. And so that's what's done in part B. And here you can see the constants of motion that result. In part C, you're asked to find a Lagrange equation of motion for the time component. The time coordinate is c times t, so that's what you're differentiating with respect to. So you take the time derivatives, you take partial derivative of L with respect to dct by detour, and then you take the partial derivative of L with respect to ct, and then you write them into the Euler-Lagrange equations and rearrange, and then you end up with an equation for d2ct by detour squared, and that's your time component equation of motion. So in the last part you have to integrate the differential equation for the time component. You do this using exactly the same trick that we've used in other examples of this type. The last bit's a little bit tricky, but it's basically similar to other questions we've done of this type. So you make a substitution for dt by detour. I've called the variable u0. This changes your left hand side into u du by dct, which is a first order equation, and so the right hand side you substitute in for the dx by detour and dy by detour terms using the constants of motion. Once you do that, the equation is homogeneous. It's just u's and ct's, and it can be done by inspection because you have sine of kz minus omega t divided by the square of 1 plus cos of kz minus omega t, and the integral of that's just 1 over 1 plus cos. So that gives you the answer. So you just have to basically do the integral by inspection. So the last bit's a little bit tricky, but I guess every question has to have a sting in the tail, and the point is you can get a lot of marks just by doing the first A, B, and C, and then getting as far as you can with D. So the students who did this question generally did rather well.